Welcome to The Explainer. Today, we're diving into something that is so easy to just take for granted. Gravity, right? We drop something, it falls. Boom. But instead of just viewing gravity as this invisible magic trick, we're going to break it down. We're going to look at it as a concrete, proven law of nature that we can actually solve together, almost like a cosmic detective story. By the end of this explainer, we'll map out exactly how humanity figured out how to literally weigh the universe. Okay, let's dive into this. For centuries, pre-Newtonian philosophers basically assumed the heavens and the earth were completely unrelated realms. Like the rules down here, say a rock falling to the ground, had absolutely nothing to do with the rules up there in space. But I want you to think about this. What if the exact same invisible thread connected a piece of fruit dropping from a branch directly to the moon suspended in the night sky? To really get this, we kind of have to look at how this idea evolved. We start way back with Aristotle in 300 BC, just making philosophical guesses that things seek the ground. But the real science kicks off around 1600. We've got Galileo taking actual physical measurements of objects falling. Then, right after him, Johannes Kepler is crunching massive amounts of astronomical data to figure out the laws of planetary motion. But here's the thing, it was all fragmented. Earth rules over here, space rules over there. Enter Isaac Newton. He acts as the ultimate cosmic detective. He takes Galileo's earthly experiments, combines them with Kepler's heavenly observations, and in 1687 he publishes the Principia. He synthesizes it all into one universal truth.
Which brings us to Section 1, the core concept, or the first great unification.
So around 1666, Newton had this absolute massive aha moment. He proposed that gravity isn't just some local Earth thing, but a universal attraction. And this brilliantly illustrates that first great unification. Think about the apple accelerating toward the ground and the moon doing its endless orbital dance around the Earth. Newton's absolute genius was realizing that the Earth pulling the moon is the exact same proportional attraction as the Earth pulling that apple. The moon is essentially falling toward the Earth, but it's moving sideways just fast enough to keep missing it. It is the exact same force, just on completely different scales.
To put a formal definition on it, Newton called this point mass attraction. Basically, every point mass attracts every single other point mass in the universe. Now, I really want to make this personal for a second. This doesn't just apply to giant planets and stars. It applies to you. Right now, literally, just by virtue of having mass, you are physically exerting a tiny, undeniable gravitational pull on the very device you're using to watch this explainer. And crazy enough, it is pulling back on you. It's all proportional to your masses and the distance between you. You are quite literally gravitationally attracting everything around you all the time.
Moving on to Section 2, let's look at the mathematical recipe and defang Newton's equation. Now, what's really interesting about this slide is that the math can definitely look a bit intimidating at first glance, right? But this famous formula, F equals G times M1 times M2 divided by R squared, is actually just a really simple, elegant recipe for how physical attraction works in nature. It tells us two beautiful things. First, the more mass two objects have, the stronger the pull of gravity between them. Pretty intuitive. Second, it's an inverse square law, meaning as the distance between the objects gets bigger, the gravitational force doesn't just get slightly weaker, it drops off by the square of that distance. So if you double the distance, you're looking at only a quarter of the gravity. So let's quickly run through our cast of characters here. F is the force. M1 and M2 are the masses of our two objects. And R is the distance between them. But there is a really critical detail here that comes directly from Newton's work. That distance, R, is measured from their centers of mass. Newton actually proved mathematically that separated, spherical objects, like planets for example, act as if all of their mass is concentrated perfectly at their exact centers. Fun fact, it took him 20 solid years to mathematically prove that one specific detail. And then finally, we have G, which is the gravitational constant.
All right, Section 3, Physical Evidence in the Lab, or how we went about weighing the universe.
So for all of Newton's mathematical brilliance, there was actually a huge missing piece to his puzzle. He couldn't calculate the true absolute physical force of gravity. Take a look at this profoundly tiny number, 6.674 times 10 to the negative 11. Newton didn't know this constant. He knew exactly how gravity scaled, sure, but without G, he couldn't give you the actual physical force in newtons. To pull that off, science was going to need to figure out how to literally weigh the universe.
Believe it or not, it wasn't until 1798, that is a full 111 years after Newton published the Principia, and 71 years after he died, that British scientist Henry Cavendish finally cracked the secret. Cavendish designed this incredibly sensitive, delicate experiment to measure the minuscule gravitational attraction between heavy lead spheres, right there in a physical laboratory setting. By carefully measuring this incredibly tiny twisting force, he provided the exact physical evidence and data that allowed scientists to finally nail down the value of g.
You just have to appreciate the breathtaking scale of what happened here. I mean, you have this totally mundane, earthly laboratory setup in the 18th century, literally just measuring lead balls on a torsion balance, and it provided the exact numerical, physical evidence required to calculate the laws governing the Earth and the Sun. A desktop experiment literally weighed the cosmos. It's just wild.
Which leads us to our final act, Section 4, When Newton's Law Fails, the Twist in the Cosmic Tale.
Because despite the brilliant math and the irrefutable physical evidence from Cavendish, our understanding of the universe is always evolving. So the crucial point is, even Newton himself suspected his theory wasn't the final word. In 1713, he famously wrote Hypotheses non fingo, which basically means I feign no hypotheses. He was actually really uncomfortable with this whole idea of action at a distance through a vacuum. He admitted he didn't actually know how gravity worked behind the scenes.
And sure enough, centuries later, the cracks really started to show in the observational data. It turns out, when things get way too massive or they get too close to each other, Newtonian physics just physically breaks down. For example, the orbit of Mercury around our massive sun wobbles by this tiny 43 arcseconds per century. It's a discrepancy that Newton's flawless formula simply cannot explain. On top of that, Newtonian physics predicts that light rays bending around massive objects should only deflect by about half of what astronomers were actually observing. And if we look way out into spiral galaxies, stars are orbiting at speeds that heavily disobey Newton's laws entirely, which is what led astrophysicists to theorize the existence of unseen dark matter.
To solve these extreme cosmic anomalies, we needed a new detective on the case. And we got one with Albert Einstein. Einstein's general relativity completely redefined gravity. In Einstein's universe, gravity isn't this invisible pulling force propagating through empty space at all. Instead, massive objects like the Earth and the Sun actually bend and curve the literal fabric of space-time around them. Objects in orbit aren't being pulled, they're simply following the natural, physical curves of the space they're traveling through. General relativity perfectly solved that mystery with Mercury's orbit and the bending of light, serving as this massive, incredible upgrade to Newton's work for those extreme cosmic scales.
Which leaves us with a truly profound realization, doesn't it? If Newton gave us the math for gravity and Einstein showed us the shape of space-time, what physical mysteries of the universe are we still waiting to discover? Newtonian gravity gives us an astonishingly accurate description for our daily lives. I mean, it's enough to send rockets to the moon. It was the absolute first great unification. Einstein then took it a huge step further, showing us the sweeping geometry of the cosmos. But the story isn't over. From the hunt for dark matter to the bizarre rules of the quantum realm, science is just this ongoing, thrilling detective story. If Newton and Einstein could fundamentally rewrite the rules of reality, what invisible physical mysteries are waiting right under our noses? Keep observing, keep questioning, and I'll see you in the next explainer.